Greetings, Mathophiles. Welcome to a video in which we will examine the product rule from calculus, which is designed to help to differentiate in situations where you have one function multiplied by another. We're going to start with sort of a visual exploration to make plausible the formula, and then we will do a couple of examples, and then if you want to click off, that's okay, but if you want to continue to the end, we'll actually prove the formula. So we have here a rectangle. And let's imagine that the length along the base is given by f of x and the height is given by g of x. So the area of this rectangle is f of x times g of x. Then let's imagine allowing f to change. And it could be growing, it could be decreasing. It's a little easier graphically if we represent it as an increase. So let's imagine that f is growing while g remains constant. And let's ask ourselves the question, at what rate is f growing? And then at what rate is f times g growing? And what happens is the added area off there to the right in red is going to be given by g, which is its height, times whatever the increment is in f. So we might call it g delta f. And so the rate at which that rectangle is growing ought to be g times the rate at which f is growing. In other words, g times f prime. And that should be the rate at which the entire rectangle, both parts taken together, is growing. You can tell a similar story about changes in g, right? So this area up above here is going to be f times whatever delta g is. The rate at which it's growing is going to be f times the rate at which g is growing, or f times g prime. You can imagine both of them growing at once, perhaps at different rates. And then it gets a little more interesting, because then we have to ask ourselves the question, all right, what's the area as a whole doing? What's the product doing? Well, we know what most of it is doing, right? F times g, the original blue area, that's constant. That tall, skinny rectangle off to the right, that's growing at a rate that is f prime times g. The rectangle up above is growing at a rate that is g times f prime. And then we have that extra little square that we haven't had to consider before. And we're going to take the position, and we'll have some good theory to back us up with this. We're going to take the position that it's the product of two things that at the margin are very tiny, and so it can be safely ignored. You wouldn't necessarily want to take that on faith without something more behind it, but we're going to see something more behind it. So it would appear from this investigation as though the rate at which the product f times g is changing, if f and g are functions, has to do with f times g prime and g times f prime, and it should be their sum, again, if we can safely ignore that little white rectangle up in the corner. Let's state this formally as a formula, then let's give a couple of examples, and then the Hardy can continue on to a proof. So here's a statement of the formula that's pretty strongly suggested by the visual investigation that we just made. If f and g are differentiable at some value x, then f times g is differentiable at that x, and the derivative with respect to x of f times g is f of x times g prime of x plus g of x times f prime of x. Notice that this expression is sort of agnostic with respect to what's f and what's g. If you were to reverse the names of your functions, so to speak, if you were to take your f and call it g and your g and call it f, and insert everything into that formula, you would find that the result wouldn't change because those multiplications are commutative and the addition across the two terms is certainly commutative. So if you were of a mind to wonder whether it mattered what names you gave to the two factors in your product, there's actually no difference whatsoever. Our first example will be to differentiate this product, quantity x squared plus 5x plus 8 times quantity x cubed minus square root of x. Now, we should observe in fairness that it's not necessary to use the product rule. you could pound out this product, collect like terms, and you'd have a sum of rational powers of x with some coefficients out in front, and you could just blast your way through left to right term by term. But the multiplication wouldn't be all that fun, right? It's 3 factors times 2, and we get the square root in there. It'd be nice if we could dodge that if possible. And with the product rule, we can. I like to not call my factors, the functions that are my factors, f and g or other letters of the alphabet. I like to just call them first factor and second factor, which means if you can restate the product rule as the derivative of a product is the first factor times the derivative of the second factor, plus the second factor times the derivative of the first factor. Saves you the problem of renaming things f and g. And when you maybe have some chain rule along with your product rule in a given situation, we see these formulas on the page in terms of f's and g's, and we hate to be shifting our perspective all the time about what's an f and what's a g. So I like to just call them first factor and second factor. So the first factor is x squared plus 5x plus 8. The derivative of the second factor is 3x squared minus 1 over 2 root x. The second factor is x cubed minus the square root of x. The first factor's derivative is 2x plus 5, and there we go. Now, it's not pretty, but it's the derivative. We accomplished the task. And if our goal was to know what the rate of change of this product was when x was equal to 1 or something like that, we could then plug the 1 in and we would be good to go. So we dodged a fair amount of algebra in order to get this derivative by means of the product rule, which you have to like. Second example, derivative of x cubed tangent x. Here we don't really have the option of doing some algebra to it first. Really, we're stuck either with the product rule or with the definition of the derivative. And if we try to use the definition of the derivative, all of us would feel anguish and most of us would fail. But it's really easy with the product rule. First factor times derivative of second factor plus second factor times derivative of first factor. You could do some things to make that nice. You could maybe do some factoring or some re-expressing the trig functions. You might be able to get it to look a little more convenient. But it's not terrible, and it's the derivative. We managed to differentiate this product x cubed tan x without breaking too much of a sweat, thanks to the product rule. So we want to know what is the derivative with respect to x of some function f times some function g, and we're assuming that they're both differentiable. Definition of the derivative says that this is the limit h gets tiny of f of x plus h, g of x plus h, minus f of x, g of x, all over h. I'm going to go through now, and I'm going to add 0 to the numerator. And I'm going to leave myself a little extra room here. And I'm going to add it in a particular way. So this is going to be the limit h to 0, f of x plus h, g of x plus h. And I'll call this out maybe by means of some color, minus f of x plus h times g of x plus f of x plus h, g of x. So of course that sums to 0, and then minus that final term up above, f of x times g of x. So my reason for doing it that way might be a little bit mysterious at the outset. It's not a thing that would occur to everyone. Somebody told me once, and now I'm telling you. Although it's gettable if you know where this thing has to be headed. If you're really sharp with sort of the structure of the difference quotient and the derivative definition. But anyway, next step is going to be to do some factoring. So this is limit h to 0. First two terms here, I'm going to pull out the f of x plus h, leaving me g of x plus h minus g of x. And then next two terms, we're going to pull out the common g of x. So that's going to be g of x times f of x plus h minus f of x all over h. And your spidey senses may be tingling a little bit now. You may see where this is going. I'm going to do a few things in this one line, but I think they're going to be such that you can follow them. So limit h tiny. I'll split these two terms up above into two different factors. So this thing over h plus this thing over h. And I'll group them in a particular way. So this first term is going to be f of x plus h times g of x plus h minus g of x all over h. And the second one I'm going to write is g of x times f of x plus h minus f of x all over h. Perfectly legitimate algebra. If I take this product and divide it by h, that's the same as if I do this division and then multiply the result by f. So we're fine. But now, let's work our way through these limits and recall that limits of sums are sums of limits, limits of products are products of limits. So as h goes to 0, this goes to f of x. Now, if you're really paying attention, f has to be continuous for that to be the case, but f's already differentiable, so we're not going to have to worry about that. The limit as h goes to 0 of this difference quotient is just g prime. Limit of g as h goes to 0, that doesn't even depend on h, that's just g of x. And finally, limit h goes to 0 of this difference quotient is f prime of x. Quite easily done. I hope this has helped you to get your head around the product rule, not only the mechanics, which are fairly straightforward if you know the formula, but also sort of why it works the way it works. So use it for good. Happy mathing.